This is Waqas Rehman, and I'm a PhD student of electrical engineering at the Missouri University of Science and Technology. And the title of my presentation is Sizing the Energy Storage System for Energy Arbitrage in Extreme Fast Charging Stations. Integration of the energy storage system with extreme fast charging stations can be valuable in many different ways. The most important applications are the power buffering and the energy buffering. The power buffering mitigates the power swings and the subsequent voltage rise and fall in the power quality of the distribution network. And the energy buffering application, the energy storage system stores the energy during the off-peak prices and discharges that energy during the peak prices. And during this process, it earns the savings as shown in this simple illustration. Therefore, optimal sizing of the storage system and optimal energy management scheduling of the charging station is extremely important for the reduction of operational cost and the investment cost while satisfying the performance requirements of the charging station and the life degradation aspects of the storage system. In this regard, this model proposes a nonlinear model which is implemented and solved in the AIMS optimization software. This slide presents on the left-hand side, the main features of the proposed model are presented. The proposed model aims to obtain the optimal energy and power rating of the storage system and also the optimal energy management scheduling of the charging station by considering the reduction of total demand charges. The total demand charges consist of two components. One is the monthly demand charge and the second is the annual demand charge. And this particular formulation is based on the realistic utility practices. Moreover, the proposed model uses an improved ESS life degradation modeling based on polynomial curve fitting, and it also uses a cumulative charging and discharging energy-based ESS cycle counting. So in the literature, we have observed that the method proposed or the formulation proposed, they assume that during a discharge cycle, charging of the ESS cannot happen, and similarly during a charge cycle, discharging of the ESS cannot happen. However, this is not realistic because in some applications, especially if you have a PV system inside the charging station, then during a charge cycle, discharging can happen, and similarly during a discharging cycle, charging can happen. But these formulations, the cumulative charge and discharge energy-based formulations, address that shortfall, and the decision vector for the proposed model is consist of the optimal energy rating, power rating, optimal depth of discharge, the annual ESS cycles, and the optimal energy management of the charging station, and the maximum monthly and annual average power imported from the grid. The objective function consists of mainly three components. The first component is the reduction of total demand charges. The second component is the reduction of investment cost, installation cost, and the O&M cost. And the third component is the reduction of the operational cost. So the cost component of the energy storage system are annualized using the formulation, using the ACF factor shown at the bottom of the slide on the left-hand side, which uses an interest rate of 4% and a project lifetime of 10 years. Some of the selected constraints of the proposed model are shown on the right-hand side. Equation number 1 presents the energy balance constraint. And for this model, the optimization horizon of 1 day is used with a time granularity of 1 minute, mainly to account for the rapid changes inside an extreme fast charging station. Equation number 2 presents the formulation to compute the average power import from the grid based on an averaging window of 15 minutes. In the second part of this equation, the maximum of the average power import for a day is being computed, and since max function is a nonlinear one, which makes the overall model a nonlinear. Equation number 3 presents the cumulative charge and discharge energy-based cycle counting method. So in the proposed model, the state of charge at the end of the day is assumed to be the same as at the start of the day. Therefore, the total number of charging cycles and discharging cycles are the same, and that will also be equal to the total number of ESS cycles. Equation number 4 presents the life cycle, the modeling of the storage system based on the polynomial curve fitting. And just in the literature, the approximation of the life cycle curve is used based on the staircase linearization or the piecewise linearization. But this method proposes an accurate are a better approximation of the life cycle curve of the storage system. The results of the proposed model are shown on this slide, where figure 1 presents the input data, which the input data consists of the charging station demand for weekdays, for weekend days, and the electricity market price curve. And the optimal energy management of a charging station is shown in figure 2, in which we can see that the light green curve represents the energy imported from the grid, and the dark green curve represents the energy charging and discharging energy of the storage system. We can see that during the off-peak prices, when the electricity price curve is at the lowest, the energy storage system charges, and it mainly discharges during the peak demand period hours, which also coincide with the peak electricity price hours. So in this process, it earns the arbitrage revenue and resultantly the arbitrage savings. So we can also see that the energy storage system also discharges during this interval and during this interval, mainly to ensure that the average power imported from the grid is minimized. So to summarize the sizing result, we can see that the power rating and the energy rating of 672 kilowatt and about 2800 kilowatt hour are obtained with an annualized savings of about 6% with a project lifetime of 10 years. And the optimal depth of discharge and the total number of cycles are about 92% and 346 cycles per year. We also did another study in which the effect of degradation modeling is studied, and we've observed that the ESS will reach its end of life in about 7 years if we don't consider the degradation modeling of the storage system in the overall sizing model, and therefore it will need to be replaced and it will incur some extra cost. Therefore, having the degradation modeling in the proposed sizing studies is extremely important. And lastly, using the storage system, the optimization model successfully reduces the maximum average power imported from the grid by about 26%, which will eventually decrease the total demand charges. Some sensitivity analyses were performed where the sensitivity of the ESS sizing and the savings in the total cost is studied is studied with allowed number of cycles and the electricity price multiplication factor and the ESS investment cost multiplication factor. So in figure 4 presents the sensitivity analysis with allowed number of cycles. And we have seen that by limiting the allowed number of cycles by moving from right to left, we can see that on the overall, the sizing of the storage system decreases, and also the annualized savings decrease when we move from right to left. And this is because by limiting the number of cycles, we are limiting the capability of the energy storage system to participate in the energy arbitrage opportunities. In figure 5, the sensitivity of the ESS sizing is studied with different electricity price multiplication factor values, which will be referred to as EPMF. So with the EPMF of 1 represents the original electricity price curve, which was taken from literature. And by reducing the EPMF factor values, we can see that the sizing also reduces, as well as the savings in the total cost reduces. And we can observe that by reducing the EPMF lower than 0.8, it becomes infeasible to deploy the storage system in the charging station. And similarly, we have varied the values of the EIMF, which is the ESS investment cost multiplication factor. And we can observe that with the EIMF of higher than 1.3, deployment of ESS becomes infeasible and there will be no savings after that point. And figure 7 presents the results of the sensitivity of sizing and savings by simultaneously changing the values of EPMF and EIMF. And for the region where EPMF is lower and EIMF is higher, in this region, the deployment of the ESS becomes completely infeasible. But for the region with EPMF of higher values and EIMF of lower values, having a bigger storage system becomes more and more feasible, and the savings also increase. So for the future recommendation, the application of the renewable sources can be investigated and uncertainty modeling and the generalization of the nonlinear model can be studied. Thank you.